We are going to compute the flux of a vector field through the upper hemisphere of radius 1. So we have just the upper half of a sphere, and we have a vector field with various arrows, and we want to know how much of that flow is going through this surface, through this upper hemisphere. And that's what we'll compute with a flux integral, which is just a surface integral on a vector field, right? A problem like this should specify a vector field and a surface and a direction. Are we talking about an outward flux or an inward flux? In this case, it says outward normal. It might just say outward flux, and we would take that to mean the outward normal. So for a surface integral, as always, we need a parameterization, and we know how to do that for the sphere. For the sphere of radius 1, we're looking at sine phi cosine theta, comma sine phi sine theta, comma cosine phi. Again, the radius is 1, so there's no other number in there. We know how to get the normal vector if we need to. We get the tangent vectors, and then their cross product gives us the normal. But we've dealt with the normal for a sphere enough, and we've been asked to remember it, memorize it. So what is it? It's r squared sine phi. So that's 1 squared sine phi times sine phi cosine theta, sine phi sine theta, cosine phi. It's a lot of similarities here, right? So that's our parameterization, and we have our normal vector. The parameter domain, probably should have written this with the parameterization, but better late than never. So theta is going from 0 to 2 pi. We're going all the way around this upper hemisphere. And phi from 0 to pi halves. Only the top half. Remember, this is phi equals 0, and this is 180 degrees. So the top hemisphere is 0 to 90 degrees, 0 to pi halves in phi. So we have our parameterization, our normal vector, our parameter domain. We are trying to compute a surface integral f dot ds. That is our flux. And remember, that surface integral is going to look like 0 to 2 pi for theta, 0 to pi halves for phi, and then f is z comma x comma 1. All right, well, z is right here, that's cosine phi, and x is right here, that's sine phi cosine theta comma 1. And we have that dotted with the normal vector, and then d phi d theta. All right, here we are again. This is our surface integral, our flux integral. We've written f in terms of our parameters, theta and phi. And we'll have the dot product with the normal vector, and then we'll be ready to integrate. So just one more thing to write. Let's go ahead and put in what that dot product gives us. The normal vector, recall, is sine phi cosine theta, sine phi sine theta, and cosine phi. So when we do that dot product, we end up with cosine theta, sine squared phi, cosine phi, plus cosine theta, sine theta, sine cubed phi, plus sine phi, cosine phi, d phi, d theta. This is what we will need to integrate in the end. Each of these is doable. The sine cubed of phi is a little beyond what we're expecting you to be able to do in this class, but it's something we could look up in an integral table, or you could ask me for help on dealing with that particular integral, but this all comes out to just equal pi. So that's our outward flux.